for your nice introduction. Thank you to the organizers for your kind invitation to this conference. So I know the name is a hard one. When I was in England here, this was almost impossible for people to pronounce it right. So Alfred is right for me. So it works before. Oh, here we are. Okay. So a brief overview of what I'm gonna do in the next 20 minutes or so. A brief introduction into exercise intensity domains and how a number of factors affect the physiological response in association with the external load, power output or speed or whatever you would like to use is applied. Effects of fatigue on the physiological response. And the second and third part will be the determination of mNIRS or the use of mNIRS technology to assess exercise intensity domains. And the third part will be some sort of case study we did during the COVID restrictions with an athlete where we have a number of longitudinal data. And this address a point that was raised at the end of the previous session, variation. So intensity domains, there are, and many of you are aware of exercise intensity domains and what the meaning of exercise intensity domains is, but there is basically a typical physiological response to these domains that is predictable, at least at the whole body measurements, but also at local measurements, we will see in a second. So typically used are gas exchange variables, oxygen consumption at different exercise intensities. And these domains are dignified by specific physiological underpinnings, thresholds, whatever you would like to call it. And it's important to have an understanding of these specifics for training and racing. So a model of these domains. So typically we use, and this was also addressed yesterday in one of the workshops, typically moderate, heavy, and severe domain. Sometimes there is also an extreme domain added, and sometimes also the lower part here, an easy domain. But basically at the very beginning of an exercise, when an exercise intensity is applied in the moderate domain, there is a steady state reached within a couple of minutes, and this remains stable throughout the exercise. This is somewhere at approximately 90% of the first ventilatory threshold, for example. And in the heavy domain, this steady state is reached as well, but this may be exceeded or prolonged up to 10 or 15 minutes, but eventually there is a steady state reached in this region as well. And the boundary between this moderate and heavy domain is typically assessed with lactate threshold, ventilatory threshold 1, gas exchange threshold, you can name it. It's basically all the same goal to assess this boundary right here. And in contrast to the moderate and heavy domain, in the severe domain, there is no steady state achieved in this example in oxygen consumption because the exercise intensity is actually too high, and oxygen consumption raises towards its VO2 max. And depending on where you work, near the heavy or near the extreme domain, eventually exercise must be limited, is limited actually, and must be ended. So this second threshold here, this second border here is of special interest for exercise scientists because this delineates the sustainable from a non-sustainable and unsustainable exercise intensity, and some estimates associated with this threshold or with this steady state is the critical power, ventilatory threshold 2, respiratory compensation point, and so on. So The second border here is of special interest, and there are, as I said, a number of estimates to come up with this threshold. So, for example, here the maximal lactate steady state, and I will not go into the methodological issues of number of these thresholds, but it's basically the last intensity where the blood lactate concentration will kept constant from in the last 20 minutes. So there's no further, no increase of 1 millimolar above 1 millimolar. And on the right-hand side, the critical power model, the hyperbola, where the asymptote of this hyperbolic relationship is the constant power. The critical power. So especially when we are talking about critical power, there are a number of studies here on a whole body level that have addressed this in the past centuries. And one of the first studies, one of the early studies from David Poole, when working at slowly below critical power, oxygen consumption remains pretty stable or reaches a steady state and can be tolerated up to the 24 minutes, whereas when working above critical power, oxygen consumption raises and the limit of tolerance is reached somewhere before. And pretty much the same is shown on the right-hand side with blood lactate. And not only as a whole body measure, but also on a muscular level, on a local level. This has been shown by Andy Jones, bless you. Phosphocreatine measured here after an initial decrease, it remains pretty stable up to the 20th minute, whereas when working above critical power, there is a drop in phosphocreatine and exercises stopped at about 10 minutes, pH and inorganic phosphate as well. So both whole body and also local metabolic responses behave like this. And this has, of course, also been shown with some mNIRS data. Here's oxygen consumption on the left-hand side. And on the right side, you see the deoxyhemoglobin, the response of deoxyhemoglobin below and above the ventilatory threshold, steady state below and slight increase here at above the ventilatory threshold. We've done some similar studies recently in youth adolescent cyclists. The deoxyhemoglobin here on the right-hand side, there is of course a higher amplitude when working in the heavy domain compared to the moderate domain, and there is also a stabilized response and even a drop, and we will come to this in a couple of minutes. But an increase here is seen on the in the heavy domain. Also on the left-hand side, the STO2, tissue saturation, TSI. The slope of the initial drop here is much steeper at the higher intensity compared with the moderate domain. So both measures, both typical measures, is it either deoxy or the STO2, can be used actually, or have been used to address these responses. Now, when we compare estimates of these metabolic steady states, so the second threshold, these are not all the same. So here in comparison is a critical power, maximal lactate state, respiratory compensation point, and also the deoxy break point. And as you can see here, power outputs are pretty different. There's a large variation here, up to 40 watts. But on the other hand, oxygen consumption at these thresholds remains pretty stable at around 3.3 liter. So the energy requirement or the energy, the ability for the body to produce a certain amount of energy is pretty stable across the estimates, but the value itself, the estimates itself, they are very, very different. And not only has this been shown across different markers, measures, but also within here, for example, critical power, it's quite busy table, but if you only focus here on the first column, you can see here critical power estimates or estimates of critical power we did, in this case in a field study during field cycling, but the same has pretty much shown by others in laboratory as well. So we used here different prediction trials or prediction trials of different duration, and also used 3 different models, the hyperbola, the linear, and the inverse model for those who are interested. And also you can see here some differences from 290 up to 300 plus watts. So there is some space, or actually some variation within an estimate as well. Not only for critical power, but also again for typically ramp or graded exercise tests in this study. You can see here different protocols, 5 watts per minute up to 30 watts per minute. And as you can see here on the x-axis, the power output associated with the maximum is quite different. And again here, oxygen, VO2 max in this case is the same. And here are the numbers. Maybe. Oh yeah, here we are. So here are the numbers again. Peak power output from 260 up to 350, and again here oxygen, in this case maximal oxygen uptake, is pretty much the same, and the same is been true for the respiratory compensation point, and this was 212 to 240, so a difference of around 30 watts. Huge difference depending on the protocol you use. But again here, oxygen consumption as a measure of metabolic steady state is pretty constant. Now, we have to consider this when we're doing tests, and the new kid on the block is durability. At least it was named in the last couple of years as durability, but any one of you are aware of that fatigue affects power output and the physiological response, of course, to power output. In this case, in this study, they applied actually and I've chosen only the graph of the 20-minute because it's more related to the second, to the border from the heavy to severe domain. And you can see a drop, obviously, in power output after a certain amount of work has been done. For sprinters and climbers, they did it. But basically, the main finding of these studies is that durability affects actually, or fatigue affects actually power output, of course, when we are doing 2 hours, 3 hours right before an effort, there is less power output available. And there appears to be a differences in more successful riders, that they are more fatigue resistant than the peers that are not as successful. Laggy. And the same here for one particular marker, the critical power. In this study, they did the control, so it was in the rested state. And the conventional method using 3 to 5 prediction trials to estimate critical power, and the 3-minute all-out test after, I think they did a 2-hour moderate intensity ride to address this, and there is about an 11% decline. So also fatigue plays an important role when we use external load and would like to evaluate a physiological response to this. Now, quick summary of part 1, external load varies. Oops, getting louder now. Sorry. The maximum metabolic steady state is a transition zone based on a number of factors we have addressed now. This is not one particular value we can use all the time, but it is affected as we've seen now. And for this purpose, a fast responding physiological measurement, that's where mNIRS comes into play, because other to heart rate, mNIRS is a very, very fast responding physiological measurement, can be very useful for life tracking, actually, for athletes on whether or not they may be sustainable in the sustainable zone or not. So We did a little study here where we assessed the deoxy profiles across intensity domains. We've used the deoxyhemoglobin and the STO2 in the moderate, heavy, and severe domain. And we would like to see whether or not we can assess profiles associated with a possibility, with a high probability of sustainable oxidative metabolism. We did it actually with at 60 and 90 revolutions per minute cadence, but I show you only the 90 revolution because there was no effect of cadence at all for any of the parameters we measured. So not shown here. Yeah, that's not as important, but these were trained cyclists, around 60 milliliters, around 5.5 watts per K. They did a graded ramp exercise test and 6-minute step transitions to moderate, heavy, and severe intensity domain. And the mNIRS was taken here from the vastus lateralis. Oops, fast. This is the protocol right here. So the square wave transitions from moderate, heavy to severe domain. And here is the deoxyheme as an example. And we assessed, first of all, the maximum change from baseline to the maximal values, which is in the heavy and severe domain at the end, last 30 seconds. But in the moderate domain, it was always, and we come to the details a little bit later, here at the very beginning. And we also divided each intensity domain into 1 minute bins to assess whether or not there is a sustainable metabolic steady state. Again, these are the results. You can have a look at this later. So now, first things first, oxygen consumption as expected and as shown previously, there is a continuous increase in the delta here from moderate to heavy to severe domain. Here are the numbers. Pretty much the same was seen here for the deoxyhemoglobin right here from 17 to 30 to 36, with all three are significant different. And the STO2 increased here from the moderate to the heavy domain. Don't be confused here. I've just flipped the graphic from negative, of course negative, but I've just flipped the graphic right here. So there's an increase from moderate to heavy, but no further significant increase to the severe domain. So it remains stable in our data right here. Now, when we have a look at the 1 minute profiles, I will leave out the VO2. There is a drop here in the moderate intensity from the 2nd to the 6th minute, indicating that enough oxygen is supplied to support the demand. There is a pretty much stable profile seen here in the heavy domain. And again here, stable with a little bit of increase, and I will come to the numbers in a minute. Whereas on the STO2 profile, the drop you can see here in the moderate domain, and there is almost no difference here between the heavy and the severe domain. Now, as a single example, this looks like this, and here in this example, the severe domain was a little bit less deoxygenation or STO2 drop compared to the heavy, and here to the moderate. So the individual numbers. So you can see here the statistics. There was a significant decrease here in the moderate domain. So the deoxyheme decreased, but you can see in all the data large variation associated in these domains. Here in the moderate domain, this remains stable. There's no significant difference. And here in the severe domain, the 5th to the 6th minute increased compared to the others. Here are the data from the STO2 response. And finally, final one or 2 minutes. This is the case study I mentioned. We had the opportunity during the COVID-19 restrictions that the subject trained in our laboratory, and we did over an 18-month period, every 6 to 8 weeks, the same transition protocol here from 150, 180 to 10 and 240. and measured the responses. And basically what comes first, you can see here that we measured the delta values here. There's a difference between the respective baseline and the maximum. And as you can see here, there is a drop in baseline, and therefore the delta, of course, changes as well, because if we would only take the absolute values here, the 4 micromolar increase, this would be pretty much the same. So here are, here is a zoom of these deltas: 2.6, 3.9, 4.9, 5.4, and this is because the baseline, the zero baseline, for example, in the severe domain is much lower because of a hyperperfusion, of course, during this period. Again, the STO2s, couple of numbers. And this is my last point. I will not go into detail, but there is a large range right here in all the numbers. And this is where the question was before. There is not only a large inter-individual variation, so between subject, but also within. So this is the same subject, and we have here number of coefficients of variation, of course, and of course the range associated is pretty large. The figure for this is the same data. So to wrap up all things, there is significant increase in the deoxy response, which is an indication of an increased oxygen and energy demand, of course. The response profiles can be used to assess sustainable from non-sustainable metabolic rate. There are, of course, and we must be aware of this large inter and intra-individual variation, so we cannot come up with one particular value. 50% STO2 is whatever. And for this reason, I guess that delta values are probably more useful than the absolute values. So thank you very much. I'm just in time. Thank you.
Thanks for the presentation. Do we have 10 quick questions?
Is there anyone? Just one very quick. So are you suggesting to use mNIRS for prescribing and monitoring exercise intensity domains or not?
Not for prescribing. No, I would not do this for prescribing, but we can track pretty good, and we can assess pretty good whether or not there is sustainability reached or not. And I have a discussion yesterday with one of the developers, because I can see, because it makes sense actually. mNIRS makes sense if we have a live tracking opportunity for athletes as well. So when I'm coming from cycling, so when we are thinking of our cycle computers, fancy cycle, so it must be available somewhere on these Garmin or whatever device we use, that we can see whether there is the intensity which I'm currently riding at is sustainable or not. And not just with one particular value, and not just they show me the number of around 60 or 48% STO2. I don't think this must be some kind of trend analysis introduced in this data field. Yeah.
Thanks.
Cheers.
I would not use the answer from the